Okay, so the participant number has been stable for some time. I think we can start. Welcome, everyone. I see a lot of familiar faces, but I also see a couple of new ones. Welcome to every one of you to Footpunch AI's second masterclass of this year, Pitfalls in Machine Learning Projects. It will be hosted by Alican. I will walk you through the structure of today. For those that attended the previous masterclass, it will not be new. It will have the same kind of format. We'll start shortly with a presentation. And during that presentation, Alican will also explain some of the challenges that he has prepared for you. So the second part of this afternoon will be tackling in small groups these challenges under guidance of one of the mentors that we have provided for you. I wish you all good fun, good luck, and Alican, the floor is yours.
Thank you. Let me share my screen. Can you see my presentation?
Yes.
Perfect. Okay, so let's start. So today I'll talk about possible mistakes, right, in machine learning projects. First, I wanted to give you real examples, right? This will be the motivation. Then I'll talk about data, signal and noise, and their relationship. The reason is if you can understand this, you can avoid, let's say, 90% of these pitfalls. So I think this is a really fundamental relationship to understand. And then finally, I'll explain the challenge. So let's start with this paper. This is possibly the most famous paper combining dermatology and AI. What they did was to, using neural networks, classify images of lesions to say if there is a cancer or not, and possibly the types of cancer. And they claim that they achieve dermatologist level classification. But a year later, they publish, the common authors here, they publish another paper and they say, we noted that the algorithm appeared more likely to interpret images with rulers as malignant. So they say, why? Because in the data set that they collected, images with rulers were more likely to be malignant. So the network learned that if there is a ruler, okay, this is probably malignant. So this shows you that the claim is possibly not true, right? Dermatologist level classification is not really the reality. And it's not just with research. We have these kind of errors for deployed systems as well. And of course, you can imagine we don't have many deployed systems running for tens of years, right? So this is a good example. This is deployed in the US for more than 10 years. And then they realized that it just doesn't bring any benefit. So this is also very important to read. There are lots of reasons. So this is not just one reason. So I invite you to read the paper. But they note, this is very important, this sentence, to understand how AI can work, we must understand why CAD failed. But I want to extend this, right? We must understand why all these projects are failing. Only that way we can build successful projects. I really like this saying by Charlie. He's an investor. So he lays down his strategy. He's trying to be consistently not stupid instead of trying to be very intelligent. And this is how we should act while building machine learning projects. We shouldn't try to use the state-of-the-art models, right? Instead, we should focus on the data, for example. You can just visualize the data and see, for example, if you have rulers more in one class than the other, right? So this should have prevented that error. So let's move to the discussion with machine learning, right? What is data, what is signal, and what is noise? Because the fundamental challenge is this: generalization. Generalization is the fundamental challenge in machine learning. So we see these failures due to under or overfitting mostly. It doesn't generalize well, these models. So why? Okay, I want to explain this instead of like abstract definitions. I want to explain this using an example. Let's say we are building a cat classifier, binary classification, very simple, 0 or 1, cat or not. And we have a data set. And I would like to ask you now that what is data here, what is signal, and what is noise? So I think you can write to the chat or maybe to the Slack and someone can read it to me. I want you to think about this a bit now. Or we can even discuss this with Bram, for example. I can ask you.
Ooh, shit. No, people can reply in the text. They can.
Okay, let's see. Can you read?
Yeah,
read
we got
that
some.
to me?
Yeah, I will. So we got one response. Signal is the cat object in the picture, and noise is the background. And from Lucas, he says ears, fur, eyes color, whiskers, eye color. So I think he's suggesting that's the signal. And Tom says data, all images in the data set, signal the cats.
Yes, but also the cats, yes, but for one image. So what is the signal here, right? You can say it's the cat object, but it's not really, right? Because let's say it could be totally different here. So we cannot just say it's the cat object, it's something else, because when we go from here to here, it's totally different. So what is common? This is what I'm trying to ask. Let's say, what is common between this and this? When you say the cat, yes, of course, but let's say, how would you define it? How would you define signal in this case, for example? Yes.
You get a suggestion from Jans, a pattern of pixels, a specific pattern. And from Ishwarya, if I pronounce it correctly, features of cat like the ears, the tails, or the legs. So
Yes.
they are both suggesting a larger feature than just not the whole cat in itself, but still a certain kind of structure in it.
Mm-hmm. So it is not an easy question, right? It is, the problem is this: we can recognize cats, but we don't know actually how we do it. So it's not really easy to describe, of course. But let's say this: the signal is catness. In a sense, the blueprint of a cat. Anything, so the background is noise, that's true, but particular properties of the cat is also noise. This is what I want you to notice. Okay, this is noise, but the eye color, this is also noise, right? Yeah, ears, but the shape may be different, but it might still be a cat. So there is, what stays the same is catness, that we are not able to define. This we cannot, because we can recognize it, but we don't know how we do it. But that is what the signal is, and the rest is noise. So now another question: can you define noise types here? What are the possible noise categories, let's say? You said background, that's true. Background is one type of noise, but there are others. So what are other noise types? You can again write to the chat.
Okay, some suggestions are coming in. Blur, fading, Color is one suggestion, and lighting.
Mhm. What else?
Not catness.
True.
So yeah, okay.
Well, let's discuss the following.
We also have a question.
Mhm.
So there's catness that is common in all pictures, and the background and some parts of the cat that's different in every picture is the noise, if I understand it correctly.
Can you read it again?
Yeah, of course. So there's catness that is common in all the pictures, and the background and some parts of the cats that's different in every picture is the noise.
Yes, in a sense, what stays the same is the signal. What changes from picture to picture is the noise. But now there is, for let's say for these three images, there is something that is noise, but stays the same for all these three images. What might that be? There are many things, probably many things that stay the same. But I want you to discover that there is some noise that stays together with the signal common to all these three pictures.
Okay, so we have the hair texture as a suggestion and the color of the cat. But I think we can already see that we have three different types of cats in this case.
Yes, the colors are different, right? So, for example, one thing that is hard to notice that the style of these three images are all artistic. So, if you use this kind of data set to train, for example, a cat detector, and then you give this as an app to people, the app images will be very different. You can imagine it won't look as nice, as artistic, as high resolution, right? So this is one thing that is hard to discover. There are many things. This is not just only one. There are many things. But I want you to realize that it's not really easy always to discover all possible noises that stay the same. So the message here is this: when you collect a data set, the proper data set should contain the signal that should stay the same from image to image, right? And the noise should change from image to image. If you have any noise that is like ruler in the dermatology example, if the ruler stays the same for all malignant lesions or most, the model will learn that, okay, this has something to do with the state of the lesion, which in reality it does not, right? So it's important when you collect your data set, you shouldn't have this correlated noise correlated with your labels. Okay, hopefully this makes you think about what data and signal and noise is. It's not easy to understand at once. I suggest you to just think like this for all your possible projects. Okay, what is data, what is signal, what is noise? Do we have the correct balance between the three? Do we have the noise, do we have even the signal inside the data set? You have to ask these questions. So here, I actually want to do one thing. So let me move on to Colab. And I want to show you, this is not an abstract concept. I want to show you with code that actually we can do this. We can generate data and see what signal is, what noise is. But to be able to do this, so if I collect the data, I don't know, I know the data, right? But I don't know what is signal, what is noise. But if I generate the data, since I'm generating it, I know what the signal is, I know what the noise is, and I know what the data is. So here I'll generate data and show you what signal and noise are. So for this example, I use Newton's second law, F is equal to ma. Let's imagine you're doing some data collection. There is an object, 2 kilograms, and you pull the object with some random values of force values between 0 and 10, 50 values, and then you measure the acceleration and you plot this data. So here notice that we know this relationship due to Newton's second law. So I can generate the data, right? You can go and collect the data, but I can also generate it this way. But in reality, probably there will be some kind of noise because maybe there is friction, right? You have a frictionless table, but it's not perfect. There's friction, maybe your measurement is not perfect. So in reality, this is what you'll get, something like this, right? And if you want to fit a line to it to describe the relationship between acceleration and F, you can just simply do this, like this, scikit-learn. And you can check what is learned, right? What is the slope of this fit and what is the y-intercept? Since we generated the data, we already know what these values should be exactly without any error. We know that it should be 0.5 and 0, right? Because this is the relationship. So we are all very close, right? Not exactly, but this is the error. So we can actually plot and see. This is the data set we had. This is the fit, and this is the signal we used to generate the data. As you can see, fit and signal are very close, but not exactly on top of each other. So this shows you the following. In machine learning projects, we have a data set, and our aim when we fit a data set, a model to a data set, we are trying to find the signal. I want you to understand this from this example. Okay, let me move on to the presentation and discuss this equation a bit more. So why understanding data is equal to signal plus noise is important, right? First, now, from this we understand domain knowledge is important. How? So when we discussed the cat example, right, you talked about the color, the background, the ear, the legs. All this is possible because we all know about cats. We are domain experts, not really the best expert, but we all know, right? Things about cats, their color, the background we understand, the possible positions in the picture, right? It could be front, top, back, whatever. All these things, the fur, is thanks to domain knowledge. So this helps us which features should go into our data set. This helps us understand even if the signal is inside the data set, right? When you look at the image, you see the cat, you know that the signal is there. This is very important. I use this a lot. Machine learning is not magic. There are many times that I've asked, that people ask me to fit a model to a data, but just by looking at it, I can see that the signal is not there. So machine learning cannot find a signal that is not inside your data. And finally, domain knowledge is very important for interpreting the results. Let's say it made some errors, right? You wanted to classify 100 cat images. You see that it makes 5 errors, and you take a look at those 5 images, and you see that, let's say, they are all white cats. Okay, then you can say, there is a problem here, there is a bias, so these are not random errors. It didn't learn. Maybe in your training data, you didn't have white cats. So you see, this discussion is all about domain knowledge. Then, understanding this helps you understand this. Data is signal plus correlated noise plus random noise. If you have this situation, you will fit the noise. So let's see this, how. So this is the first case I described in Colab, right? This is your data generating signal. It generates these data points, and when you do a fit, you try to approach the signal. But if you have this case, this is the picture. You have a signal. If you have correlated noise, this is your data. And if you do a fit, this is what will happen. Even if you collect millions of data here, this is very important, right? More data won't solve your problem here. If you collect more data, your fit will be just stabilized, but there is this difference between fit and signal still. So let's see how this can happen in real projects. So yeah, this is what you fit, right? If you do this, you fit this, not the signal. If you have a systematic measurement error, if you have confounding, or if you have some kind of train test information leakage. For example, you are measuring temperature, but if your sensor is measuring real temperature +1, this is the situation you have. Or confounding, it's the paper I showed. The ruler and the malignancy are correlated, but there is a confounder, that is the dermatologist. Dermatologist thinks that, okay, this looks like a malignant tumor, so maybe I can put a ruler to take a proper image, right? So they are not really correlated. They are correlated by confounding. In that case, again, we have this because you're fitting the ruler, which is noise, not the signal, that is malignancy. And then finally, let's say you have 10 images from a patient. And if you do a split like this, right? If 5 images go to training, 5 images go to testing, what will happen is particular properties of the patient, that is, again, correlated noise. It has nothing to do with the disease, right? Just the patient has these properties. With these, we can make good predictions at the test set because still we have the same patient. So the proper split should be like this. This 10 images should go to training, exclusive or testing. Finally, I want you to realize that in your development, during your development, you have certain distribution of your data signal noise. It should match with your use case. As I mentioned in the cat example, if you have like good looking cat images, right? Very artistic, very high resolution. Then in the use case, if you are using it as an app to take random pictures of cats, it's different, right? Everything will be different. Your signal will be different. Your noise is different. You take, for example, your images with a good camera, and then you take the images with your phone with a bad camera, for example, right? This is a very good example, ObjectNet. I really invite you to read this paper to understand how this can affect the performance of your model. And finally, I want to go beyond this. Data is signal plus noise is very important. Yes, there are things you have to think about beyond this. First one, all models are wrong, but some are useful. What does this mean? I want you to, I'm not gonna explain it. I'm just gonna say, whether it is a physics model, a physical TMA, or it's a machine learning model, it's a model. That is, there is a gap between the model and the reality. I want you to realize it, right? This is why it says all models are wrong. And this gap is due to your assumptions while you're building your model. So you have to think about those assumptions. I want you to think in systems, right? Okay, we are building models, but highly probably if someone is gonna use this model, it will be part of a system. So it's important how this model reacts to the other elements. You have to think about this. This is visible in this paper. For example, doctors had a false sense of security. When the cat was there, they trusted the system more than they should, right? They didn't consider this. So real life problems, this is not equal to data science problems. In real life, we have high level problems, high level things to solve, like we want to improve patients' lives. This is not a data science problem. We convert it to data science problem. Like, okay, I want to detect in mammography this. But then when you do this conversion, again, you make assumptions. So you need to validate those assumptions. You need to test. Now, with this, we can move on to the challenge. Any questions up to now?
I don't see any at the moment.
Okay, I'll be here, so we can just discuss it later. The challenge, the theme is COVID prediction from chest X-rays using a neural network. It's based on this paper. And I have 3 challenges for you related to this paper. So first one, imagine you're a data scientist working in a company, in a research group, whatever, and you're assigned to a project that wants you to do COVID prediction from X-ray images using neural networks. What would you do, right? How would you design this project? You are a responsible data scientist from start to end. Specifically, I want you to think about, okay, the first steps, very first steps. What would you do? Then the data set. Are you going to use an online data set? Are you going to collect it in collaboration with a medical doctor? If you're going to use an online data set, which ones? Maybe you can just search for some online data sets. How are you going to build the data set? I want you to describe it, right? I want you to describe your model. This might be the least important thing here. Now, I mean, we all know, right? It could be a neural network, ResNet, whatever, right? So, but still, it's nice to, so I want you to describe it from start to end. So what would you do? And finally, how would you evaluate your performance, right? So are you gonna do a train test split? Only 3 data sets, 4 or 5, or are you gonna do a cross validation? If so, how? How would you, what else would you do, right? Just do a train test split and look at your accuracy on the test set. Anything else you're gonna do? I want you to describe this as well. So the second challenge, I want you to peer review this paper. I don't want you to be lost in details, right? You can do a peer review for hours, but just like the basic points. If you want to, there's a platform, PubPeer. You can put like your public peer review there. This is totally optional, but yeah, I think I really like this website. That's why I wanted to know about it. And finally, it is one thing to, okay, show the flows of a paper, right? But then another thing to prove it. So I want you to prove that the model in the paper is overfitting. You can either describe it or you can even code it yourself. This is up to you. So to make it simpler, in the paper there are 3 classes. To make it simpler, you can still prove it. I want you to think as if it's a binary classification task, negative versus positive, right? In the paper, it's negative, positive, and pneumonia. There are 3 classes, but you can still prove it like this, just by considering a binary classification. And finally, an optional challenge. This is a paper we published a couple of months ago. You can peer review this paper as well. And I hope that you won't be able to find flaws in the paper, but let's see. You never know, right? This is optional as you wish. So that's it. Now we can move on to the challenge. You can always reach me via email, Twitter, LinkedIn, but I'll be here for the next couple of hours. Thank you.
Thank you, Alican, for the presentation. I thought it was really interesting. If there are any questions, you can ask them now over the chat, or you can unmute yourself. And otherwise, we will have a small break and be back at 14:20, so 15 minutes. This gives us the time to divide you in breakouts, groups, and then you will be working on these challenges.
Hi, this is
Hey.
Aishwarya here. So I have a quick question. So is it
Sure.
like, can you show the challenges again, because it was so quick and the slides went off. So would you be sending the slides for the...
Actually, I can, yes. During the break, I can discuss this with Bram and then send you the... So let me show you. Can you see my screen?
Yes.
Yeah.
Can you maybe take a screenshot for now, and then we'll send you the presentation? Would that work?
Yeah, I have taken the screenshot of this page.
The next one is this.
Yeah.
I have, let's see if it works.
Actually, you already have the presentation, Bram, right?
Yeah, I'm uploading it to Zoom right now. So I hope then you can all download it. And then you immediately have all the slides, all the pretty cat pictures as well. So.
And is it like after the 15-minute break, we will start working on these, and whenever we have any doubts, we will just send a message in the chat? Will it go like this, or do you have any more concepts to explain?
So you will be divided in breakout rooms, and then you will be working on these challenges. First, your team will focus on challenge 1. There is a mentor in your room, so you can ask questions to them, and otherwise they can contact Alican for extra information if necessary. Then we will come back to this plenary session, discuss the first challenge, our findings, and then we will do the same for challenge 2 and challenge 3.
Okay.
Okay, so the file is uploading, but it is coming your way. So we'll see you back in a small 15 minutes for the challenge.
I also uploaded the files to the project on the platform. So if you go to the event on the platform, on the right side, you'll have the resources, and there also you can find the presentation now.
All right, thanks.
They also have the paper, right?
That's also on there, yeah.
Okay, because it's not open access, they cannot just click the link and download it.
Let me check real quick. MHCove.net PDF, yeah, it's also on the platform.
Okay, great.
You need the link, I'm sending that in the chat as well.
Okay, so see you in a bit.
Good.
işte dahi kapalı bir hesap para göndericileri de gitmemiş oldu.
Hi, Inchi, I think I pronounced it. I see that you've joined later, but we've already started the challenges in groups. So I will put you in a group so you can also work on the challenge as well.
Okay, welcome everyone. You have now been working on the first challenge, and I'm really curious to find out what you came up with. Maybe it's easiest if you just go by the different groups. So if group 1 can speak up one of you and tell the general findings or the general project structure?
We're group run, right?
Yeah.
I'm group 2. That's all I know.
Okay, so yes, we our first steps were contact the hospital or doctors to gather some data, see if there are publicly available data sets.
Maybe good, Dorian, to share the doc. Everybody can look with the
Sure. Yeah. Okay.
with us.
So just share the whole doc or share my screen now so everyone can see it.
Yeah, share your screen.
Okay. All right. Everyone
Nice.
sees this now?
Yeah.
All right. So yeah, this is where we're left. Then we're gonna probably ask a domain expert to participate and with him describe the goal for research and decide when their model is successful. Yeah, further we do some literature study to see if there are similar X-ray studies we can learn from. Then let's say we find 5 data sets and we decided that it was hypothetically gonna be something like this. So we get 3 open source data sets. For example, one with only COVID pictures, one healthy lungs, one 2080, and we get from the hospitals, we get this. Then how will we continue? Well, first we came up with, okay,
Can
first
I
we
ask
need to...
one thing here? 2 hospitals, you
Yeah.
said. So one hospital, 500 pictures, and the other hospital, 100 pictures, or something else?
Yeah. Yes, that.
Okay. Just wanted to make sure.
We were making stuff up at this point.
It's fine, yeah.
Okay, so the first thing we wanted to do is compare the data sets to see if they are consistent, to check for the correlated noise, if that is similar within the X-ray pictures. So check for quality, color, those kind of things. Then check the labels, for example, if they're binary classified or categorically or different in any way, and then probably deal with those differing labels and check for missing labels. And then to come back to comparing the data sets, that's where we had a big discussion, because if for example the data set with only pictures of COVID, it has just a little bit of a different color than, for example, the data set with the healthy lungs, then we don't want to just combine these data sets, because our model is then going to learn that different color stands for COVID, and that's not what we're trying to find. But we were not yet really to a good solution for this. We did decide that we need to balance our train set with a nicely balanced COVID and healthy lungs. Yeah, that's the same. Yeah, that's how far we came.
Thank you for sharing. If anyone wants to comment on it, feel free to do so. Maybe you can ask the group why they chose for a certain approach.
Yeah, I have one question.
Oh, sorry, go ahead.
No, okay. Like, how do you think you can make sure that a hospital gets 500 healthy participants to make a CT scan? Because how do you think you get those people to volunteer to put into a CT scan and get a picture? You thought about that?
No, we didn't thought about that yet.
So maybe I think this is what I understand from the statement is like 500 pictures of healthy lung doesn't mean that these healthy lung pictures are taken, I mean, after the COVID pandemic. It could be even the previous records of images which shows healthy lungs, and if the patient has signed the declaration that they are okay to share their data to hospital, then yeah. So these could have been the history of images that have been collected, yeah, even before pandemic. Yeah.
I think the question here is that why would a healthy person go and take X-ray of their lungs? Is that the question here?
Yeah, basically.
Yeah, so to answer to that, it doesn't mean that the healthy person go and take a X-ray test. It means that the person could be healthy or he could have a COVID or whatsoever. Because of this suspicion, he goes and check, but actually he doesn't have COVID or he doesn't have any other illness for that case, and his lungs are healthy. So we should understand that way.
Or maybe we could also look at pictures of other conditions which don't generally deal with chest congestion, but the patient has to take an X-ray of his lungs. For example, fractures and stuff like that. They don't generally deal with chest congestion, but they have to take an X-ray anyway.
I think in that case, we would get the problem of correlated noise again if there are fractures in the image.
No, I think the idea was that people can come in for that, but they don't necessarily have any fractures. But then we still have the data, or is that not what you meant?
For now, it's easy.
Yeah, something similar. We just need a factor for the patient to take an X-ray, regardless of whether he or she has an issue with their lungs. And from that data set, we could probably take the healthy ones out.
It's of course useful to be very skeptical here, right? And ask the hospital, how do you know that these are healthy? So validate this assumption. But I guess so that would be a nice step actually in the preparation. But for now, there are many ways, of course, to get photos of healthy lungs, right? Just asking people to come over. Indeed, there are many different conditions that you can have that they check this X-ray to see if you have a lung condition, any sort of, and it appears that you don't. So there are, of course, many ways to collect such a data set. For now, we just assumed this is the division of different data sets that we got from our research in the first steps.
Okay, clear. Since we have two other groups, I suggest group 2 shows their proposal.
I can share my screen.
Yeah, thank you, Tom.
Okay, so we actually found a data set for with COVID infected lungs and normal healthy lungs, and yeah, we thought that we need just a data set of COVID and non-COVID. So other diseases are also yeah, okay to be in the non-COVID data set. Yeah, because that would make the model too complex if it can differentiate between different diseases. So that I think that it would not be the goal. Also, in the data set, there needs to be different degrees of lung damage, because the model needs to know if the lung damage is from COVID or is from something else. And yeah, the images are labeled, so that's called supervised learning. Yeah, we didn't actually get to the model because we didn't have a lot of time. And yeah, the discussion was also mainly centered about the robustness of the model. So check the model on images it has never seen before. And there needs to be, for these images, a difference in X-ray machines, a difference in technicians, a difference in resolutions of the images itself. And yeah, other variations like male, female, and the age. And these are all things that you need to worry about.
Yeah, thank you for sharing. Again, open up for comments or discussion to this approach.
Have you thought about how to deal with the size of the data set? Because it's quite small.
Yeah, the data set itself is quite small, but we found this one example with a quick check, so we are convinced that other data sets are also available. And,
yeah, also from the original paper, we downloaded, well, I just downloaded that data set, and there's about 1,000 pictures there of COVID-19, normal, and pneumonia. So I'm sure that'll solve our data set size problem.
I just have a question for Alican here. So actually, suppose if we have a data set, not just in this COVID case, but in any case, suppose we have a very, very small data set, then how can we deal with that problem? Then can we build a very, very simple neural network model with just some one hidden layer or two hidden layer and just say very few neurons? And can we proceed addressing that problem? Or what is the ideal way to deal with a very small data set? Suppose the case is like we cannot collect any more images. How can we actually go about that problem?
Well, it depends on the application. So let's say the thing is this. First question is, can you use transfer learning or not? This is the first question you need to answer. So if your images are similar to ImageNet, let's say, and then you are able to use transfer learning, that can bring you a very big advantage. But nevertheless, so the problem is mostly testing. You need to be kind of sure that you are doing well. So if it's a critical application like healthcare, I would suggest just don't do it until you have more data. You don't deploy it or don't use it on patients or whatever, right? If it's a simple in the sense that nothing happens if you make wrong predictions, I don't know, a simple measurement setup, you're doing home project, then you can just deploy it and then try to collect more data. In any case, you need more data, right? But this way you can just deploy it. Your wrong predictions are not costly, so you can get more data and even do an analysis on the errors. But in a healthcare setting, if you don't have it, there is actually a paper doing this with 50 images, 25 COVID positive, 25 COVID negative. It's better if you don't do it, right? It doesn't help anyone. In that case, don't do it. So this would be my suggestion. There is no way to deal with it in a proper way in such a critical application. Does that answer your question?
Yeah, thanks a lot. So I also have another questions. So in the slides you mentioned that there could be correlated noise like ruler attached to the tumor, which affects or influences the model's training and prediction, right? So suppose if you have data only like that, can we add some kind of random noise to all the images, like a blur or something like that, and can we neutralize the effect of this correlated noise? Will this be neutralized by adding random noise, or
Definitely.
Even though we add random noise, the correlated noise will still be there in the image?
Definitely you can do this. It depends, of course, on the correlated noise, right? What it is, yeah. So let's say it's the ruler case, and the rulers are kind of at the edge of the image. You can simply cut it, right? It seems like a simple solution, but it will work. Or you can if you can simulate data, this is actually an approach I used. I kind of like simulated, I added real data together with simulated data to do this, right? To get rid of correlated noise, or like you can add ruler to the negative case as well, for example. If you can make a ruler without a background, you can add that to the image, and consider that, okay, you dealt with it. But there you need to be very careful, because they show that actually from the edges, if you're overlying it through simulation, not by real images, the neural network can still detect the difference, right? Because you simulated it, the edges are not perfect, then it might still find it out. So you need to be very careful, but this is possible for sure.
Like, may I know like what type of tool or library used for simulating the images?
I just use pure Python. This because so I mean I cannot explain it because it was a physics project. It was a complicated. So we were building a microscope. They were viewing a sample, and I was trying to simulate how the sample might look like. Actually, they didn't even have the labels, so I created the labels somehow, and then trained with simulated labels, and it worked interesting. So, but it's too complicated to explain. Not that it's confidential.
Yeah, I understand. But I'm just wondering, like, because if you want to simulate or generate an image of tumor, then you should have some domain knowledge on that, like how it looks like, right? I mean,
exactly, definitely. This is what you should do. Yes, this is what I did in physics. I had an expectation how the sample should look like. I actually used noise that is taken from the microscope and combined it with simulated data, etc. So you definitely need to use domain knowledge. I mean, in the case of tumors, you can. It's not. I don't know. Like it wouldn't be very easy to write tumors. But the ruler example, you can do it. Kind of. You can cut it simply, very simple, right? Just cut it. So you have avoided that problem, for example.
Yeah. Thanks.
Sure.
Okay, that's clear. I think group 3.
Take it if we yes, if I ever make a mistake, jump in, guys. We actually didn't make the notes in a different document. We typed it in the chat, but we still memorized it for the most part. So for the first step, we wanted to have a large data size with a lot of variety as well. So not just in the Netherlands, because you have different variations of the COVID virus, but from the whole world. But then it's also important that the noise is the same, so to say. So not that, for example, in Australia, they always write on the file, so to say. And in the Netherlands, we never write on it. We need to make sure that those things they have the same standards. So a varied data set with the similar standards, that's like the cutoff thing. And for the model, I will say this wrong, so team, help me here. Recurrent neural network, right? Recursive, I mean.
Oh, convolutional.
Convolutional network. Thank you. On top with SVM, I think, which I think Carsten can explain a bit better why we have 2 models.
Well, we didn't quite come to a conclusion yet, but if we would use the convolutional neural network to gather the features and then classify, like plot them, and then classify those using a support vector machine. That was basically our setup.
Yeah, exactly. And then for the evaluation, I'll share my screen real quick for my beautiful paint drawing. So when you see my mouse, right?
Yeah.
So this function here, this is the error rate for your training model. As you start to add more features or more layers in your neural network, you'll start to overfit. And then when you test it with your final test sets, you will get a large error. However, you can split the data in 3 sets. You have the test sets, or you have the training sets, the cross-validation sets, and then eventually the test set. And then with help of the cross-validation sets, you can already see when you start to overfit, because when you overfit, their error will increase. So this way you can see that you can choose features that are not too simple but not too complex, so you get basically the optimum parts where you reduce your error for the eventual model for like the testing set. yeah, that sums up what we found, what we concluded.
Okay, thank you for sharing. Based on the time, I want to ask Alican if he has a takeaway that he wants to share from this first challenge.
Well, the takeaway is it worked great. Thanks a lot for this discussion, because normally before preparing a challenge, I make all kinds of assumptions and it doesn't work. This time it worked. I really enjoyed the discussions. It was all, there is no correct or wrong answers, but there is like a correct direction, and you were all discussing the correct stuff, right? So I really enjoyed it, but I don't want to explain too much now because I don't want to give any spoilers. Maybe I can talk after challenge 2. So important thing here is that I saw that one group included domain knowledge, right? That is very important. Most of the groups, almost all, discussed the data set. In my group, group 2, they were like looking at the images just by visually trying to understand. So this is very important. This is really nice. And then the evaluation with the external tests. These are very important. So, but I don't want to explain more at this point.
Okay, then we'll leave it at that.
Yeah.
Demi, if you can set up the breakout rooms again, then the teams can work on challenge 2.
Yes, I will start it now. See you back again soon.
main point.
Okay, that's a very valid point. So very nice. Group 2.
Okay, yeah. We found a couple of things. For example, we had the problem with the way that I enhanced images. That was done with an algorithm, but that algorithm, that was the first time it was used with X-ray images. So we thought that could also be, wasn't investigated properly, for example. And we had some more, but other people are going to talk about that. Jim?
Right, sorry. I can't find Zoom. Oh, can you stop sharing your screen?
Oh. Okay, yeah.
Can I? Cool. So can you see that? Am I sharing the correct screen?
Yeah.
Okay, cool. So yeah, so we had a look at just the pictures, and this is from the COVID positive case. You'll see there's a little D there, and it's got written text. Okay, so that's some noise. This one has arrows on it, so it's more noise. Here's another arrow, and it says R.
And to clarify, this is only from COVID-19 patients.
Yes.
Taken. Yeah.
Yeah, and here you can see a bra strap in the middle there. And here we've got some ECGs running across there, and also it's written day 1 on the picture. And some more ECGs and a random B down there. So that's the COVID-19 positive case. And if you go to the healthy people, see, they all have an R in it, so our model could easily just say, oh, there's an R in it, therefore they are fine. And all the pictures look very pretty. You see, there's no ECGs, no bra straps. So yeah, then you question the data that this model was trained on. And that's everything from my side.
I believe, Abhishek, you also wanted to share something, right?
Yeah, about the convolutional window. So I'm actually pretty new to this. I was just reading about it, and it appears that that could be an important factor in determining the accuracy of the overall model. I'm not sure, but based on what I read, that's what I could come up with.
Yeah, so the kernel size you meant, right? For the convolutional operation.
Is that the same as the convolutional window or convolutional layer? I'm not familiar, I'm sorry.
Yeah, maybe you should share the document so we have some visual aid.
Otherwise, we can discuss it and maybe after group 1 has also presented their findings, and then we can have a general discussion about what we all have found.
A quick question first.
Oh yeah, of course.
So I think it was Tom who shared a screen. Tom, you mentioned at the point that.
Oh, sorry, I can't hear you properly. But
oh, sorry. Is it better now? Or still
a bit, but I try my best.
On the enhancing of the images, if we would take the issue that you are. The issue that you might find is that the enhancing of the images itself is going to give problems, right?
Yeah.
Could it be the case that if you just also enhance all the images that you want to classify using this model, if you use the same approach, then if it goes wrong, at least always goes wrong in the same way? Or is that not the case?
Yeah,
It's
that's
also more of a general discussion.
yeah, that's a good point that you make. If you just enhance all images in the same way, you don't introduce bias in the data set because the mistakes are made in the same way, I think.
Yeah, I'm not sure. That's it's a real question. Not like
Yeah, I haven't thought about that as well. That's good, but
Yeah, do you guys think so as well?
Actually, when they say enhancing the images with the algorithm, I think they mean just increasing the threshold and making the blacks really blacks and making the whites really whites for the. Sorry about all the noise. That's my.
No worries.
He knows the right time to blabber. All right. So it's about making the blacks really black so that you can have a good foreground and background separation. So I think that's what they mean by enhancing the images.
Okay, yeah, thank you. If nothing
but
else,
yeah, I have one point to make.
Yeah.
Maybe the algorithm enhances only certain features. So if there are only certain features in COVID-19 X-ray images, and the algorithm does something wrong with those features, then it can, for example, give problems. But maybe that's a bit too unlikely or too unspecific. But
depends on if it's signal or correlated noise, right? So if it enlarges the effect of correlated noise, that would be a bad thing. And if it would enlarge the actual features that you would want to see in COVID-19 pictures, that would be a positive thing to do such pre-processing.
Yeah, true, yeah.
But I think that you both made like valid points. It is weird that they don't argue why they use this algorithm. They just say like enhance. That should be good anyhow, but you could of course easily run the algorithm without enhancement and including enhancement and then say, okay, I should or should not do it. And indeed, since it has never been used before in this way, there's no reason not to use it, but at least then to argue why you use it.
I believe they do actually, like you said, check for with the normal data and with the enhanced data as well, the difference. I thought that was their approach. But maybe I'm wrong.
Yeah, I don't remember it correctly. Did they use both the enhanced and the non-enhanced in one training cyclus?
Oh, that could also be.
For the neural
I
networks?
thought they wanted to compare the influence of enhancing the data.
Yeah. Okay, that's something that we'll have to dive into. It's definitely worth discussing. It's a valid point that both sides made as well.
We could also look at removing the text from the images.
Sorry, can you say that again?
We could also look at removing the text from the images.
I believe it doesn't say anything about pre-processing the data except for the enhancing, so that's definitely something they could have done as well. Okay, I'd like to give the word to group number 1.
Yeah, we had mostly the same as group 2. We just didn't download all the data, but we came up with the same argument from figure 1 from the paper. Oh wait, I'm gonna share my other screen so you can see this. Here you can see that the COVID-19 images have a bold R in the picture in the middle, or like in the left top corner. And for example, normal pictures, it's already in the middle and it's not bold and it's in different sizes. So yeah, we already came up with the idea that probably the letters in the images would influence the outcome of our learning.
I cannot see your screen. Is it working for anyone else?
No.
Oh,
No,
okay.
it's not showing.
My story clear?
Yeah, the story.
Yeah.
Okay, then yeah, it's basically the same as group 2. So.
Yeah. So, but one other point that you also made was about the accuracy, right?
Oh yeah, we thought a 99.4 accuracy was a bit suspicious. So yeah, from what I learned, everything above like 98 or 97 should ring some alarm bells.
Yeah,
So,
almost too good to be true.
Yeah.
Okay, thank everyone. Thanks for sharing. And now I would like Alican to give feedback on these first 2 challenges.
Could I ask one question real quick about the 100% accuracy rate, for example? Like, is there no way that you can make a model of, say, a complex real-life problem, so not a super easy system? Like, there's no way you can make a model that's 100% accurate, or at least very hard.
By definition, you cannot make it because, as I said, all models are wrong. There are assumptions, right? So your assumptions will be violated at some point. You test your model on hundreds images, like just 100. Okay, maybe you can get 100%. But then the more you test, 1,000, 10,000, at some point you will reach a violated assumption, and then it will make an error. So there's no way to get it 100%, 100.0000, not possible. This is the problem with self-driving cars right now. They are trying to achieve like 99.9999, and each 9 is harder than the one before, and they're stuck. Like, I mean, you cannot just, and even if you kill one person, it's just like, you know, it's a very big problem. Yes, it's a very small error in terms of the percentage, but it's a very big cost. So now they are kind of stuck with this issue.
Yeah, I got one more question, but I'll save that till the end so we can move on.
Okay.
Yeah, do you know what's the error of a human driver? Just out of curiosity.
I don't know, but here it is also, I mean, it's not fair to compare just the accuracy, but also the types of mistakes, right? Because if you check the Tesla crashes, there are like some crashes that like so obvious. I mean, you see the truck from, I don't know, 1 minute earlier, right? You just stop, but the car doesn't stop, just crashes. So you cannot really argue that, okay, I mean, the accuracy on total is higher, but it's somehow still unreliable. If you can make such a mistake, broad daylight, no rain, no traffic, how can you hit a track that you see like kilometers before? I don't know. Like, this is another thing to consider, the quality of the mistakes, right? But I don't know really a number in terms of accuracy. My feedback would be at this part. It was great discussion. You discovered one very significant error, right? It's the collection of the data set. But there is another one that no group mentioned. So this is a single author paper. The author is a computer scientist, and there is no medical doctor in this project. Okay, you might say you can still achieve good results. Yeah, possibly. But then I actually called 2 doctors and asked, like, I have no idea. Like, can you really predict COVID from X-ray images? This is the first question you should ask, because this is the thing, right? Data is signal plus noise. Do we have the signal inside the X-ray images? You can think like, because COVID, it's a virus, right? You don't see the virus in the image. It's virus causes something, and you're trying to hope to see it via X-ray. So there is already a leap there. And then we know that there are asymptomatic cases, right? You do the test, it's COVID positive, but there's nothing in the lungs. So from here, it seems like, okay, a bit fishy. But then I asked them, they are surgeons. Maybe I should ask a radiologist as well. But they said, really, I mean, maybe you can, but definitely not 99%. Yes, maybe you can achieve 70% accuracy, let's say. Like you can discover some kind of correlation. But they said they wouldn't expect to discover such a signal from X-ray. Maybe if you use if you use CT, it might, they said it might give you a little bit more information, but their conclusion was this was not a feasible project to do. Right? So this is the domain knowledge side that you should have also. I mean, I learned this in 2 minutes. From Twitter, I sent a message to my friend. What do you think about this paper? Can you really predict COVID from X-ray images? And she answered like, no way. I mean, of course, so I cannot judge it. I still don't have the domain knowledge, right? I cannot judge it myself. So, but still, I would have designed the study considering this, right? This is a very important information. Maybe she is wrong. I mean, it's also possible, but still then you should have a very hard proof to prove her wrong, right? So this is what you should have considered as well. But the data problem, it's very correct. As you showed the images, you can just by eye understand this comes from that data set, this comes from this data set. So that's a very big problem. Yeah, so congrats.
Yes, good job, everyone.
Now in challenge 3, the point is this. So, okay, we can see it like qualitatively, we can say it's overfitting, but can you prove it really? Can you describe a way to prove that this guy is overfitting? You can code a neural network if you want. I mean, I just wanted to put this as a challenge because maybe some of you want to do a coding challenge. But main thing is I want you to describe a way to prove that this is overfitting. I don't want to give you any more hints at this point, but yeah, you have to discover it yourself.
Okay, sounds like a plan. Demi, can you divide us up again? And then the teams can work on their final challenge of today.
Yes, good luck.
All right, welcome back for the last time in the general meeting. Let's discuss your methods to find out why the article or the model in the article was indeed overfitting. So group number 2, you haven't gone first yet. So
okay. Our first idea was to, our biggest idea was to remove the lungs entirely and leave the text only, because somehow the model encodes the information, the wrong information, I believe. So we wanted to check if it actually looks at the lungs. So so if you remove the lungs, you can see if the model again predicts like 99% accurate, then you know it was overfitting. And then if that doesn't work, we wanted to remove the text on the data set, because maybe it somehow looks at the text still. And then we wanted to check if the images wanted to check the model with images it has never seen before. But model always has is less accurate when it sees images when it has never seen before, but yeah, you can try that. And lastly, we had the idea of showing it images of COVID, of asymptomatic COVID patients. So yeah, those were our ideas.
Okay, thanks for sharing. Group number 1. Can you share it as well?
Yeah, we pretty much had the same idea. So by either blurring out the actual lungs or placing something to cover the lungs in the picture, we could check if the model would still obtain such a high accuracy. And if that were the case, then that would indicate that the model has learned to classify the images based on the letters and the annotations in the image. And our other approach was to validate the model on data from a different source that did not contain these contaminations, and that would also probably yield them a worse result.
Yeah, to add to that, so when we train the model with this data set and perform validation and check to see if the training error keeps decreasing but the validation error keeps increasing for this model which is already trained, then I mean for this model which they have been used for classification, then I think that would also imply that the model is overfitting. Look at the training error and the validation error.
Can you repeat that? You do this without changing the data set, or?
You use this data set for training, but you validate on a different COVID data set. Okay. And check to see how it performs on the validation set. So when this model, what they're trying to develop is the training error keeps decreasing, but the validation on that data set, the validation error on that new data set, it keeps increasing. Then at that point, we could see that the model is overfitting, right?
Okay. Yeah.
Basically, look out for the generalization error based on a new validation data set. And also, I had this idea of calculating the variance. So we would have a true line, right? So basically, if you assume this to be a binary classification problem and you want to fit a line or you want to fit a linear line to it, then you would have a true line. I mean, based on a model which is trained on a different data set, or you would have a true line, and you have the fit from this model, the line from this model, and if the variance seems to be very high, because when a person who has COVID, maybe based on Europe, and a person who has COVID based on Asia, they will have similar properties. It doesn't depend on, what I try to tell is it doesn't depend on data. So if you have the true line, the true distribution, and you have the distribution from this model and try to calculate the variance of this distribution, if the variance is too high from the true distribution, then from that, can we say that this model is overfitting? Because one factor for a model to overfit is that it has a very high, for it to have a very high variance, right? Is it possible to do something like on that lines, or?
Yes, it is possible. But the thing is, it will still fit the same noise. I mean, variance, I'm not sure if in this case you can get that. For example, I mean, if you do different models, it might still learn. So the shortcut is always there, the noise. Probably it will still exploit it, whatever model you use it. So the variance might not indicate overfitting like this for this data set, for this case specifically.
So you say that suppose if the data set is clean and proper, then we could consider variance as an indicator for
Exactly. Variance, you can use it like in proper data set, right? Then you can say, okay, you compare your training error, test error. But here, the fundamental flow comes from the data set itself. It will exploit it whatever you use, right?
Mhm. And we also had another thought. So they have this, the authors have come up with a model, right? I mean, so if you calculate the number of parameters in this model, and we see that the authors are using like around 1,000 images in the data set. So if the number of parameters is too high compared to the number of samples used, so from that we could tell that the model is trying to fit all the points in the training images. Could we draw some conclusion like that, or
Not really, because again, it's about the test. So if you do things correctly, you can still, for a properly collected data set, even with a large model, you can get the correct fit, not overfitting, not underfitting. There are other methods, right? You can do early stopping and then get a correct model, even though the parameters are quite a lot.
Yeah, you're right. Yeah.
So it's not, I mean, it's a way, right? But it's not as clear as like putting a black square to the lungs, for example, or just realizing that the data sets are coming from different sources. These are much more like strong evidence for overfitting, I would say.
Yeah, thank you. Thanks. Yeah.
One more point that was mentioned as well, I think by you, Jari, but I'm not fully sure, is since those are fully convolutional networks that are used, that you could also construct like a feature map, right? So a feature important map.
And to see, like, are there only like a few features that really determine whether someone has whether a picture was positive or negative, because they have 1,000 features, but maybe only a handful of those actually make a difference.
No, but mainly like if it focused on the R's, etc., right?
Yeah, something like that. So that is a main contributor.
Yes, on an image, you can see actually where the neural network is looking, more or less, like not very precise, but then if it's looking at the text, then it's clearly overfitting. So
I'm also getting a point now. So suppose if we try to visualize the activation map or plot a heat map on the output of the, not on the final layer, but on maybe some last few layers. And if we see that the feature that contributes to label that image to be COVID, if it depends on the text, if there is more heat on that part of the image which contains text, then we could tell that this model depends on the feature from the text, but not on the feature from the lungs, which is in the center of the image. Maybe by visualizing the activation map or the heat map also, we could tell that how the model is able to label that image to be a COVID or not COVID, right?
Yes, this is very similar to it.
The last group was group number 3. Yes.
Correct. So yeah, basically, we found similar things as the other groups. Like you want to test to see if it's overfitted, to reduce the signal and see if you can focus on the noise, so to say. Our idea was to check the R and like place it different places and a few other things. But yeah, no new things other than the other groups have said. But yeah, while I'm speaking, super thanks to Fruitpunch for the organization. Like, it was very terrific. Good afternoon, well spent. And to Mr. Noyan as well, very insightful. Like, we talk about this in our group as well. The good insights that you get from this, aside, like in the universities and such, you get good mathematical insights, but here you get taught the intuition, and I think that's super valuable. That's something you don't easily get taught at like from dull books with lots of formulas. So good job. Thank you.
Thank you very much
for your feedback. So Alican, I think we can see that all the groups had the suggestion of like blocking the lungs.
Yeah,
which is-
that's the solution. Yeah, it's perfect. Yeah, like there's not like one solution, but this is really a clear evidence. And I shared the paper. This is what just they did. And from here, you can also see, like you can do machine learning research, right? You came up with this idea. If you had this before them, maybe you could have published a paper just by this simple idea, right? I mean, they detail a lot of other things, but this was the core, and you were able to come up with it. So you can turn this into a paper as well, right? So I think that's a good take-home message for you as well. I shared the paper. You can check the figure 5, and it's what they are doing, just putting a black skirt to the lungs.
Okay, yeah, great job. Everyone was able to find or come up with a decent solution to this for this problem that we have found during the second challenge. If any one of you has any questions content-wise for Alican, speak up now or email him later.
Just, yeah, I'll share my email again. You can always reach me, add me via LinkedIn, Twitter, whatever. Yeah, I'm open to discussion.
Yeah, it was a very great session. Yeah, usually the session would consist of some theory and hands-on. Yeah, but this was kind of different with challenges, which we tend to overlook. Yeah, so we think that we know how to train a model and how to evaluate, and we think like, okay, we know how to work with neural networks, but this challenge made us to rethink whether we have understood everything correctly and we are following the process basically, like from the beginning, from the first steps till the end. Yeah, it was very nice working in these challenges. Thanks a lot, everybody. Thank you. Yeah.
Thank you.
Great to hear. Then if there are no questions, then it's indeed time to say farewell. I want to thank everyone for coming. A huge thanks to Alican, of course, for hosting this masterclass. Thanks to our mentors, Sako, Cecilia, Demi, me, yes.
Thank you.
Thank you.
And if you want to know more about Fruit Punch and the activities, because this was not a one-time thing, we do this more often. We try to organize things like a masterclass or something in that trance every month. Please subscribe for the platform. I will post a link now in the chat. If you have not, oh, that's a private message to Demi. Yeah. And tomorrow I will send you all an email containing a review form, and it would be really appreciated if you could fill that in so we can improve it for next time.
Last question. What's the reason why you host these masterclasses? Is it just to advertise? I mean, it's not a bad way to advertise the platform, but is that like the main goal? But it's okay if it is. Just asking.
Is this question for me or Bram?
Both.
So, Alican, why are you giving this masterclass?
Well, I like teaching because it's not easy to convey complex ideas. It helps me learn myself these ideas, right? I mean, you can always assume, oh, okay, I understand this, but once you try to teach it, you see that, okay, you really don't understand it. So this is my main motivation doing this. I learned myself a lot from teaching. With Fruit Punch, we did also AI code, lots of sessions for now. Until now, in maybe a bit more than a year, we did more than 10 events, I guess, with me. So, I mean, it was really valuable for me. This is my motivation.
Did that answer your question, or? Okay. Yeah, you're welcome all, and I hope to see every one of you at our next event.
Thank
I'll
you.
bring friends.
Yeah,
Thank
bye.
you.
Bye.
Yeah, thanks.
Bye.
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 Bye. Thank you.
Bye. Thank you so much for the session.
You're welcome.